This video is on waves. So remember, waves transfer energy. That's the main thing that you need to remember, is that waves transfer energy from one place to another. Whether you're talking about sound waves or light waves or radio or x-rays, waves are going to be transferring energy from one place to the other. There's two different types of waves. You have mechanical waves and you have electromagnetic. Sound is a type of mechanical wave, so mechanical waves need a medium in order to transfer their energy. A medium is anything that has molecules, so solids, liquid, or gases all have molecules, so they need to travel in something that has molecules in order to get their energy to go from one place to the other. Electromagnetic waves are like light waves. They can travel through nothing at all. So here you have the difference between mechanical and electromagnetic. The first ones we're looking at are mechanical waves. Again, mechanical waves need a medium in order to transfer their energy from one place to the other. You have two different types of mechanical waves. You have transverse and then you have longitudinal waves. Transverse waves are also called perpendicular waves. So you have the energy moving from side to side, but the wave itself is going up and down. So they form perpendicular lines, which is why they call them perpendicular waves. Longitudinal waves, on the other hand, are called parallel waves. So you have the energy again moving from side to side, but the wave motion itself is also going from side to side. So this is like if you were to pull back on a slinky and let it go, you would see the rings on the slinky get pushed together. Once the energy flows through them, they'd get spread apart, and you would just see that continue to happen the rest of the way down the slinky. These are pretty easy waves to remember. So you have where the slinkies are pushed together, that's called compression. Where they're spread apart, that's called rarefaction. So here are the two different types of waves. Again, transverse waves are moving up and down, whereas longitudinal waves are moving side to side. Okay, transverse waves have a lot of different parts to them. So transverse waves have the top part is called the crest, the bottom part is called the trough. Okay, frequency is a number of cycles per second, so you need to be able to first identify a cycle. So that would be like one wavelength. So again, you measure the distance from crest to crest or trough to trough. That would be a wavelength. And so I can count how many wavelengths I have in this 1 second time period. So if I start here at the trough, the very next wave, that same spot on the next wave, that would be a wavelength. So that would be one cycle. So there's 1, 2, 3 waves in this 1 second time period. So the frequency would be 3 hertz. The amplitude is the distance from the equilibrium. So I'm measuring from the equilibrium or the midpoint up to the crest or down to the trough. That would be your amplitude. The period of a wave is the time that it takes to complete one cycle. So again, here would be one cycle. I would be looking at the time that it's taking for that one cycle to occur. That would be the period. Wave speed is frequency times the wavelength. So remember, as the frequency is increasing, so the more waves you see in a 1 second time period, the closer the waves are going to be together, so the wavelength is going to decrease. So they're inversely related. So you have your formula again, frequency times the wavelength to solve for the speed of the wave. Okay, we talked about standing wave. So this is how a wave would look if it was traveling along a fixed object. So like a guitar string, when you pluck a guitar string, this is how it would look. So you can see here right down the middle, that would be at its equilibrium or its midpoint when no energy is flowing through. Once you pluck it and energy is flowing down the string, it would look something like this. Here you have the antinodes. So that would be this pushed out section here. So this distance would be like the amplitude, how much energy is flowing through the wave. And then these little pushed in sections, that would be like where the resting point or the midpoint is, and that would be a node. One wavelength of a standing wave, you pick a node and then you draw the letter S. The distance between those two nodes would be the wavelength. We talked about wave interaction. So this is when waves are interacting with other materials. You have reflection, refraction, diffraction, and absorption. Remember, reflection, the wave cannot pass through the object, so it bounces off of it and goes into another direction. You have refraction, so this is where the energy flows through the object, and because there's a change in the material and a change in the molecules and the speed of the speed of the wave actually changes, and so on the other side, the wave is bent in another direction. You have diffraction, so the energy cannot travel through the object, so it just goes around any holes or openings. Here's another example of diffraction. And then absorption. is when the energy goes into the object and either is completely absorbed, so all the energy gets trapped into that object, or it comes out smaller the other end. So the amplitude and the amount of energy that the wave have would come out the other end a lot smaller. Okay, you have wave interactions. So this is what happens when waves interact with each other. So you can have constructive or destructive interference. Constructive interference is when the waves meet, they combine to make one larger wave pulse. So that happens when they meet crest to crest or trough to trough, they'd form a larger wave. And then in destructive interference is when a wave pulse is overlapping each other, but they overlap on opposite ends. So you have the crest meeting up with the trough, that would cause destructive interference, and then the waves would just continue to move down the pulse or the string that they're traveling on. In terms of energy, okay, the higher the frequency, so the more waves you have in a 1 second time period is going to increase the energy, and so would the amplitude. The bigger the amplitude or the bigger the distance from its equilibrium, the more energy that wave is going to have.